In this video, we're going to talk about amino acids, amides, and chirality. The very first amino acids identified were found in 1806 with the discovery of asparagine by Louis Nicolas Vauquelin and Pierre-Jean Ribiquet. They had identified this thing, asparagine, from asparagus juice. Now, they didn't understand the structure of it, but they had discovered it and isolated it as an individual chemical. It is not responsible for turning your urine into something that smells like asparagus. That is something else entirely. But keeping that urination theme, it was in 1810, only a few years later, that William Hyde Wollaston discovered cysteine, a chemical found in bladder stones. It was something that our bodies, when they malfunction, was not reabsorbing out of our urine and was concreting inside human and animal bladders. There is a very large one. You do not want one this large. In fact, stones like this, kidney and bladder stones, has been the cause of death before we could identify that they were there of many people, including Sir Isaac Newton. And just 10 furthermore years, Henry Braconnot was looking at gelatin, the derived colourless, flavourless protein that comes from animal collagen. Basically, they melt down the hooves and the harder parts of animals like pigs, and they extract this protein called gelatin. It is the ingredient you add to make jelly and to set certain food substances. It's present in sweets and marshmallows, for example. Now, Henry Braconnot was able to identify a chemical that came out of the gelatin called glycine. Now, we now know this to be the simplest of all amino acids, and he also was the first person to understand that the proteins were breaking down into simpler units, and that this new isolated chemical, glycine, was one of those. By the mid-19th century, chemist Adolf Strecker created something that we now call the Strecker synthesis, and it was a way of creating alanine from raw ingredients. Now, this wasn't the isolation from a natural source of these amino acids. This was actually synthesizing it, creating it from raw ingredients. And so throughout this process, he was able to gain a glimpse as to what was present inside amino acid molecules, and he found that they contained two key and common functional groups. They all contained the amino group, the NH2, and they all contained the carboxylic acid group, the COOH. It is when we have both of these together in the same molecule that we have an amino acid. Now, we have to be careful with the names. People do get confused at this point. Amino refers to the NH2 group. Amino acid is when we have NH2 and the COOH group. But where it gets complicated is if you think back to when we were talking about amines, those molecules that contain the nitrogen-carbon bond, so there's a nitrogen attached to your hydrocarbon somewhere, then if that nitrogen is attached to the very end carbon of the chain, so that the last nitrogen has got just the NH2 group, then it is called a primary amine. And as soon as we move that nitrogen to one of the carbons that's mid-chain, we start changing the naming convention around it to include the word amino before the name, because it has an amino group halfway along. That doesn't make it an amino acid. It is only an amino acid when we also have the carboxylic acid group as well. So how do we name amino acids then, if we don't name them like that? Well, it depends on what sort of amino acid you are, because there are in fact different classes of amino acid depending on how far away those two functional groups are from each other in the carbon chain. If the amino group, the NH2 group, is just one carbon away, then we would call it an alpha amino acid, like this example here. The carboxylic acid group is there on the left. There's one carbon and then the amino group. And having just one carbon in between means it is of the first order. And we call it an alpha, in this case, glycine. Glycine is the old name for it, it's the common name. The IUPAC name for this would be 2-aminoethanoic acid. If it wasn't just one carbon in between, but two carbons in between, then we would call it beta. In this case, beta alanine, which is 3-aminopropanoic acid in the IUPAC naming convention. And then this one down here, which has got 3 carbons in between, is gamma aminobutyric acid. And you can see that basically this is how we classify it, with an alpha, beta, and gamma, which refers to just how many carbons there are between the two functional groups. It's important to know the general formula, and this is quite straightforward. With an alpha amino acid, there's only basically one carbon in between the NH2 group and the carboxylic acid group. Now, it could be that that carbon has whatever else it's attached to. It could have a side chain at this point, and that's what the R represents. It could have some other thing in it. But in terms of just this chain of the hydrocarbon, it has NH2 group at one end, COOH group at the other. It has a carbon, a hydrogen, and something else. Now, that something else could be another hydrogen, in which case there'd be nothing else to this, or it could be a methyl group or some other such thing that is attached to it. But the general formula is this for an alpha amino acid. And for a beta amino acid, you can see that basically we've got the NH2 group at one end, we've got a CH2 group, and then the next one, CH, something else, and then the COOH group at the end. Now, why is this all so fascinating to us? And it's basically because these amino acids are the building blocks of proteins. We are made of proteins. Our cells, it is their function to create proteins in our bodies. So it is the alpha amino acids that are normally the ones that are the building blocks of our bodies. Beta amino acids are not normally found in proteins, but some are important to life. They have important biological roles. B-alanine, for example, is in vitamin B5, which is pantothenic acid. It is an important amino acid for keeping us healthy and well. Now here we go on a side quest into the world of biology. So if you're doing biology as well as chemistry, then you will encounter quite a lot of these. Glycine there, the most simple of all amino acids, and then alanine, and then they go on. We're going to bump into others like leucine and things like that. Aspartic acid, it plays a very important role in the urea cycle. Now what I'm going to do, I'm going to allow you to go and read these all yourself. And if you're interested, is go open a biology textbook. We need to focus on the chemistry of these substances rather than their particular uses in the human body. Now, this slide starts with basic properties of amino acids, and I don't mean they're just basic as in simple. I mean basic as in they're a base, as in an acid or a base. Now, let's have a look at this. This molecule here, this glycine, it'll be the one that we use quite a lot. You can see that it's got these two functional groups, the amino acid on the right and the carboxylic acid group on the left. Now, what we know from our study of the carboxylic acids is that lone hydrogen at the very end of the carboxylic acid group is vulnerable to being given away. It has a hydrogen dissociation constant that means it's probably the first to go of all of the hydrogens that could dissociate on this molecule. And being able to donate it, it means that this molecule can act as an acid, and indeed that is why it is called an amino acid, is because of the carboxylic acid group. But the NH2 group on the other side, in the same way that we've seen before with other things like amines, they can also accept a proton in the form of an additional hydrogen. And so it can also act like a base in that it could be a proton acceptor. You can see just down there, an ammonium salt, we've got an additional hydrogen has connected to the nitrogen. It's basically formed the ion ammonium, and you can see there's a little N+ in there. Now this behaviour of being both able to donate and to accept a proton is sometimes called amphiprotic, and a very good example, apart from these amino acids, things like water, because of course water can donate a proton, it can also accept a proton. But amino acids are perhaps the most interesting example of this kind of behaviour because it has an effect on their later chemistry. So as well as acting as a base, it could also act as an acid, and we could have that H+ remove itself from the COOH group. Now, if we mixed it in solution with something like sodium hydroxide, it could undergo a neutralization reaction. It would form a salt, in that we would lose the hydrogen, the whole molecule would become negative, the positive sodium would be attracted to it, and if we dehydrated it, if we took it out of solution, then we would end up with these salt crystals, which can actually form. This salt here, sodium 2 amino ethanoate, sometimes called sodium glycinate, is one of the main ingredients in makeup removing foam. If you've ever smeared any of this on you, it is one of those main ingredients in that. So it is actually a very useful industrial and cosmetic product. Now, when previously we looked at the derivatives of carboxylic acid, we looked at the process of esterification, the forming of an ester. If you remember, that's one that has an oxygen in the middle of the chain. But what we had to do, we had to take a carboxylic acid like ethanoic acid, and we had to heat it with an alcohol. And the OH group at the end of the alcohol would basically eliminate water. It would dehydrate water out of the middle of the molecule, and so then we would have two carbons joined to that central oxygen just there. Now, this will happen with any carboxylic acid, of which amino acids are an example, a specific, unique example, but it can happen with those as well. So here we would have to do the usual thing. We would have to heat the alcohol in the presence of sulfuric acid so that we have lots of H+ ions floating around, and we get this. You can see it's an ester on the left. It is like methane on the left, and on the right it is just like glycine. And so it's formed around the oxygen there. And so we would call this methyl 2 amino ethanoate, which does have a common name. Now, why is this important? Is because this is an actual type of polymerization. It's a biological polymer joining things together. Now, these carbon-nitrogen compounds joined together, they have a special name in chemistry. We call them polypeptides. Now, you might have heard of polyester. Now, polyester is joining lots of esters together. Well, these biological molecules that also contain nitrogen, that are peptides, we call these polypeptides. And there are chemicals that you might have heard of that are mixes of polypeptides, insulin, for example. A zwitterion. This is an example of a zwitterion, this down here. The name is German. It comes from the word Zwitter, which I think if it was German we'd call it Zwitter, but don't quote me on that. It comes from the word hybrid or hermaphrodite even, which means the best of both worlds. You're going to have it being both a proton donor and a proton acceptor. It could do either. It could even possibly do both at the same time. It could even donate a hydrogen to itself somewhere else. In the fact that the oxygen could lose it and the nitrogen could gain it, it's more likely, in fact, to just gain it from the surplus that might be in solution, the solution with which it finds itself in. Now, the whole molecule is neutral. It doesn't have an overall charge, but one side of it definitely has a charge relative to the other side. But this is subtly different from having an electric dipole. It's not that the location of electrons around those atoms are going to create a partial positive charge on one side of the molecule relative to the other. One whole atom has an entire electron missing, or has an electron gained, the equivalent charge of which, by this proton donation. So where a proton has disappeared, the relative charge of that area is now -1 because +1 has left. And the other end, where a proton has been gained, the relative charge of this area is now +1 because a proton has been gained where there wasn't one before. Now, why should we care? Like, what is the actual point of knowing about it being a zwitterion? Well, it actually has an effect on whether or not it's going to behave like an acid or like a base. For all of these amino acids are going to have something called an isoelectric point. Iso coming from the isos, which means equal. It basically means this, that there is a level of pH that affects whether or not it is, if it is in a solution of this pH, it is going to act itself like an acid or a base. And here it comes. If the pH is greater than the isoelectric point, as in more alkali, then it will behave like an acid. and donate a proton to the alkali mixture. So if you put it in something that is an alkali, it is going to act like an acid in that instance. And here I've got a list of some very common ones, and you can see the isoelectric point there. Let's talk about amides. Now, we spoke about amides on the presentation where we were looking at the derivatives of carboxylic acids. And what they had this structure. They had a carbon double bond O attached to the nitrogen. And so that there, ethanamide, which was a primary amide. Remember, it was when we spoke about mouse urine, the smell of mice. It's when we took something like acyl chloride and we reacted it with ammonia. And basically we swapped out the chlorine for the NH2 group and formed some of the products along the way. There were 3 different types, primary, secondary and tertiary, depending on just how many carbons were attached to that central nitrogen. Now what we could do with an amino acid is we could do basically the same thing. We could have that nucleophilic attack of the ammonia come in, swoop in, swap out the OH group of the glycine of this carboxylic acid group and substitute itself. And now what we've got on one side is an NH2 group, and on the other side we've got what remains of the amino acid. So in here we've now got 2 NH2 groups attached. Glycinemide. Okay, strange name. But this is an example of a peptide. We've basically extended this through this process to be a polymer. We've basically made this hydrocarbon longer. We now need to talk about the shapes and very specific locations of the atoms in these amino acids. And to do this, we just need to revisit chapter 11 for a second, where we spoke about structural isomers. Now, structural isomers, they have the same molecular formula, but different structural formula. So here is an example, ethanol and dimethyl ether. Both of them have got 2 carbons, both of them have got 6 hydrogens, and both of them have only got 1 oxygen. But they are very different chemicals. It's just a different configuration of the same atoms. Now that is a structural isomer. It gives them different chemical and physical properties. Now keep that word in your head. It's going to be important on the next slide. Different to structural isomers are optical isomers, a relationship between 2 very similar looking molecules that make them enantiomers. Enantiomers coming from the Greek, meaning that they are opposite parts. But what does it mean to be one? Well, the definition is that you are non-superimposable mirror image of each other, just like your left and right hands. You can see that if I took my left hand and I superimpose it across in front of my right hand, I cannot superimpose it. It is a mirror image. Now, we sometimes find that molecules are like this too. Take a look at lactic acid down here. Now, just for a moment, I want you to imagine if you could take hold of the CH3 group on the left-hand side, that little methyl group, and you grab it by that and you rotate the whole molecule, so you've flipped it over onto its back, then the OH group that is sticking out towards us should now be sticking out away. Now, if we look at the molecule on the right-hand side, it almost looks the same. But what we can see is that the CH3 group has been moved to the right, but the OH group is not facing away, it's actually facing towards us. That's a totally different molecule to the one on the left. It's its mirror image. And so what we would describe is that the carbon, around which we can rotate this, that is connected itself to 4 different groups of elements, it is the chiral center. It is the point about which we can rotate this molecule. To be a chiral center, to have chirality, you need to be bonded to 4 different groups of atoms, and glycine, our favorite, number 1, our simplest amino acid, is not like this. You can see that the carbon there in the middle is right in the middle, so not the one that's in the carboxylic acid group, but the one that's up rather than down, if you can see what I'm looking at there. It has got an NH2 group to the right, it has got a COOH group to the left, and it has got 2 hydrogens coming from it. It means it's only got 3 So we've got three different things because the hydrogens are the same as each other. So there are no natural enantiomers, none at all. There are no optical isomers of this. That if I flipped it the other way around, it would just look like this from the back. And there's no other versions of this that are mirror images of this. But if we go to the next amino acid in the tree of complexity, alanine, it's an alpha amino acid, and the carbon that is right there, immediately adjacent to the carboxylic acid group, you can see that it is attached to four different groups. It's got an NH2 group to the top left, it's got a carboxylic acid group to the right, it's got a hydrogen as well, and it's got the methyl group sticking out the bottom. Now, whether or not it is the hydrogen that is sticking into your face and the amino group receding away into the background, or it is the amino acid group, the amino group that is sticking in your face and the hydrogen that recedes into the background, that depends on whether or not it is L-alanine or D-alanine, or whether or not it is this enantiomer of this chemical or that enantiomer of this chemical. The two are mirror images of each other. Notice again that the chiral center on this diagram is depicted as a little star. And also notice that with these, the three-dimensionality of this structural formula needs to be represented somehow. We need to show that one of these is sticking out in our faces and one of these is dropped away into the background. Now, we don't normally have to annotate which one is particularly dropped into the background, but because it is very specific that the amino group here is basically defining what this chemical is, we've defined on this left one here that it is receding away into the background with the sort of broken triangle, if you will, representing the bond receding away. But the solid black triangle is it coming towards us in our face. We're going to see that, and whenever we see this, stars and the blocky bonds in triangle shape, it indicates to us that there's probably going to be some enantiomer action going on with this molecule. The more complex amino acids, those are the 19 that are involved in making proteins in the human body, they are all optical isomers. They all have enantiomers of themselves, and they have different properties and have different functions. Here's a nice example. Leucine, as you can see here, it's 1, 2, 3 is 4 carbons long in the chain attached to the COOH group, but it's also got this methyl group on the second carbon. It is, as you can see, it's an alpha amino acid because the NH2 group is joined adjacently to the carboxylic acid. Now, whether or not that amino group is sticking forward or away changes the nature of this amino acid. D-leucine is the powder that's found in dry inhalers, whereas L-leucine is found in protein shakes, and most specifically in Huel, that brand that is always advertised. So what does this D and L mean? Well, it's from the Latin levus, meaning left, and D meaning dexter, meaning right, dexterity, for example. And what you're going to have to do is, for a structural formula like this or a skeletal formula like that, is you're going to have to identify the chiral centers. So on this particular example on the right hand side, the chiral center is just there because it is attached to carbon in one direction, a methyl group in another direction. It's going to be attached to a H, and it's also going to be attached to the amino group. It's the only part on that entire molecule where an individual carbon has 4 different groups attached to it. That is the chiral center, and around which the NH2 could be drawn, coming towards us or going away in the background to draw the D or the L versions of that molecule. It is very important, if there are 2 optical isomers, that we understand which one we've got. If we're synthesizing a drug, for example, that the physical, chemical, and biological and medicinal properties of the optical isomer of the chemical we're trying to synthesize might be very different from what we're hoping to achieve. This famously occurred in a morning sickness medication called thalidomide in the last century. Now, thalidomide has 2 optical isomers, L and D, sometimes called R and S. And just pausing there, why L and D and R and S? Well, you should know this, there are two different ways of identifying these. L and D is what's called a Fisher projection. It comes from the Latin for left and right, but it's also possible that Carn-Ingold pre-log projection could call it R and S, where R means rectus and S means sinister, meaning like left-handed. You sinister people out there. But anyway, coming back to this, thalidomide, the D-thalidomide was marketed and prescribed as a drug to treat people that were pregnant, to treat their morning sickness. But what was not controlled was the amount of L-thalidomide that was present in that medication. Teratogenic, it means it was causing birth defects that were not realized. It was not identified that it was this drug very early on. Even when it was identified, it wasn't withdrawn from the market nearly soon enough. Severe birth defects, it caused loss of pregnancy, it caused children being born with organ damage, limb malformations. 10,000 children were born with severe birth defects as a result of not getting this right. That's more children that have been born with birth defects than both of the atomic bombs and all of the radioactive leaks that have occurred in human history from this one medical mistake. And so there we have it. You don't need to know the details of thalidomide, but it is very important for us to remember that one optical isomer may be very different from the other, and we should pay very close attention whenever we see a carbon with 4 different groups attached to it.